cosmological phase transitions. Okay, now so the YouTube live stream is up and running.
Yeah.
Very good. And I think, yeah, it's time to get started. So we'll start with the first talk by Chiara Caprini. We're very happy to have you with us today.
Thank you.
Chiara just told us that she's still physically in Paris, but she will soon move to her new position in Geneva at the University of Geneva and also at CERN. So here at CERN, everybody's very happy and is looking forward to you coming to Geneva. And yeah, so Chiara will give a review talk of 35 minutes plus 5 minutes for questions. And then you will talk about the generation of gravitational waves from kinetic turbulence. So please, Chiara, the stage is all yours.
Okay, thank you very much for this invitation to talk at this meeting. I'm afraid it is not going to be really a review talk. I'm actually presenting new results, so I sort of didn't understand that this was meant to be a review talk. I hope it's okay, but you'll tell me. I mean, okay, so actually I'm presenting some new results concerning the gravitational wave signal from freely decaying kinetic turbulence. And this is based on work in progress that is done in collaboration with Pierre Auclair, PhD student in APC of both Daniel Stier and myself. And then Daniel Cutting, Mark Hindmarsh, Kari Rummukainen, Danny Stier, and David Weir. Okay, so let me first start with some motivation of why we care about this topic. So, I mean, I'm sure all of you assisting to this workshop are aware of this, but still. So here I have this axis that represents time going forward in the universe and, you know, in the early universe. And basically, I'm representing what we know already through a sort of direct proof from either photons or other kind of particles. And what we know about is recombination, of course, through the CMB. We know about Big Bang nucleosynthesis through the measurement of light elements, and we know indirectly about inflation through CMB anisotropies. But as you know, there might be quite a wide range of scales between the inflationary scale and the BBN. And these scales, we have no access with electromagnetic radiation, and yet there are pretty interesting phenomena that we believe might have occurred at these energy scales. And so gravitational waves, actually the interest of gravitational waves is that they might provide access to these otherwise dark epochs of the early universe evolution. So in particular, we expect the occurrence of some phase transitions in this period. And here I have highlighted these are here because it is sensitive to the electroid scale. And this is what I'm going to show in a bit. First, let me show also this cartoon. Here we have the omega gravitational waves as a function of frequency today. And this is basically all what we know or will know in the near future about the stochastic background. We have terrestrial interferometers that can access it. CMB is an indirect measurement. Obviously, pulsar timing arrays with this very interesting recent result by the Nanograph collaboration. And here you see LISA sitting here around the millihertz. And if I zoom to this zone, so obviously the sources of gravitational waves differ for each of these frequencies. And by zooming in the LISA window here, so this green line is the LISA sensitivity. Here you see a cartoon showing all the sources that LISA can actually measure. The one with the highest signal to noise ratio are obviously massive black hole binaries. There is the galaxy, stellar origin black holes, but here you see, it is taken from this, review, very nice review. Here you see this little bump here, which could be some extra noise due to a phase transition in the early universe taking place at the electroid scale. So how does it work? Well, in this context of the primordial universe, we can think of gravitational waves as tensor perturbation in the Friedmann metric, and then one perturbs the Einstein equation around the Friedmann metric, and one sees that the wave equation here for the gravitational waves is basically sourced by the tensor anisotropic stress, which would be the tensor component of the perturbed energy momentum tensor of the universe. So this is what we want to look for if we want to study, forecast sources of a stochastic background of gravitational waves in the early universe. So some process generating tensor anisotropic stresses. Turns out that this might occur, so the production of these tensor anisotropic stresses that that act as sources of gravitational waves, this could occur at the electroid phase transition. Okay, so the electroid phase transition, here you have a cartoon of the universe, the history of the universe, right? And this occurs around, let's say, 100 GeV, and it's a bit our sort of boundary between tested physics, at least the test of the standard model of particle physics, and somewhat the unknown, let's say. So it is very interesting that we can have also a gravitational wave signal from this particular epoch in the universe evolution. Now, as you all know, so phase transition can go about either smoothly as a crossover, or as a first order phase transition if there is this potential barrier that develops between the false vacuum and what will be the true vacuum, right? And within the standard model of particle physics, the electroweak symmetry breaking is a crossover, so there won't be, in this case, any gravitational wave production, because gravitational wave production is possible only if from a phase transition that is first order, or better say, potentially measurable gravitational wave production, or visible gravitational wave production is possible only in the context of first order phase transition. But it turns out that there are several well-motivated scenarios that go beyond the standard model of particle physics, in which the electroweak symmetry breaker is indeed of first order. And so if we have then gravitational wave production associated, which turns out to be of the right amplitude to be visible for LISA, then this constitutes, a very strong case for the LISA mission, because it means that LISA could provide some sort of extra test of the electroweak symmetry breaking and of beyond the standard model particle physics. Now, how this proceeds? So the first order phase transition, there is the generation of these bubbles of the true vacuum in the false vacuum C, and towards the end of the phase transition, they collide. And it is precisely this collision that gives rise to a tensor anisotropic stress that sources the gravitational waves. So the tensor anisotropic stress can be either directly from simply the gradients of the scalar field. So really the bubble wall here, this is where the scalar field has a non-zero gradient. So this can directly act as production of gravitational waves, or we can also have the presence of a fluid motion. And this is due to the fact that in general, this scalar field that is undergoing the phase transition will be coupled to the particles of the early universe that are in the surrounding, let's say, the bubbles. And so as the bubble wall expands and sweeps through this plasma, the coupling sets the plasma into motion. And this motion can arise, as has been demonstrated, we will see, in the form of sound waves around the bubble walls, or possibly in the form of turbulence. Okay, and in this case, the anisotropic stress is simply some velocity distribution, okay, that happens to have a transverse stresses component. Then furthermore, this fluid movement arise in a fluid which is actually fully ionized. So one does expect the fact that if there is turbulence, this turbulence will be of the magnetohydrodynamic type, so accompanied by magnetic fields. And in this case, magnetic fields, so here I have the electric one as well, but what I want to say is that the stress energy tensor of an electromagnetic field has a tensor component by itself always. So you see that there is a very rich phenomenology of sources that can lead to gravitational waves at the first order phase transition. And in particular, what I haven't been saying clearly up to now, but okay, I sort of hinted to up to now, is the fact that if the phase transition occurs at the temperature of around 100 GeV, we get a gravitational signal in the millihertz region, so exactly where LISA is sensitive. Why? Because as you have seen, these tensor stresses, the production of these tensor stresses is all related to the presence of the bubbles, and in particular to the bubble collision. And therefore, the typical gravitational wave frequency that we expect will be connected to the bubble size. Okay, so here I define this parameter epsilon, which is a bit the ratio between the bubble size and the Hubble scale at the moment of the phase transition. And, you know, this parameter epsilon can be, you know, for example, of the order of a few %. And in this case, we are exactly in the millihertz region if the temperature is around 100 GeV. Okay, so there is a pretty strong case here for an interesting signal. And here I show a note plot. Again, a gravitational wave amplitude as a function of frequency. The red line here is the sensitivity curve of LISA. And this black line here is the possible signal from a BSM scenario, okay, the X portal scenario for some for values of the phase transition parameter, okay, and here you see this peak that I was telling you about that occurs at a frequency which is about corresponding to the inverse, obviously, of the interbubble separation or bubble size, let's say. And here you see two components. So the black one is the sum, and we have this component from the sound waves, which is what you know would arise. But there is also this turbulence component, MHD turbulence. And now what I want to present you is revision of these old results that is shown here, which is very, very old and was based only on analytical study, and we have revised this recently. I mean, we are finalizing the paper. Okay, so let me now concentrate on turbulence. Now, what is turbulence? First of all, some generalities, right, and why it is expected to occur in the early universe. So in general, we call turbulence some phase of chaotic fluid motion. And so as opposed to laminar flow. And it presents, in general, both a dilatational component and a vertical component. Okay, so this would be a divergence-less component, and the dilatational would be a component in which the velocity has a divergence, the velocity field. Now, in general, we expect turbulence when the advection term in the Navier-Stokes equation is larger than the diffusion one. And this is represented by the Reynolds number. And we say turbulence occurs whenever the Reynolds number is larger than 1, because it means that the non-linearities that are connected to advection term overcome the viscosity in the fluid, okay? And so the Reynolds number is in general, so the root mean square velocity, so the average velocity of this chaotic fluid motion times some particular length scale that here I call psi. So Reynolds number depends on the scale, depends on the RMS, and depends obviously on the kinetic viscosity. So the smaller the kinetic viscosity, the higher the velocity, the bigger the scale, the most we have the possibility of having turbulence. And now if we insert some values, okay, so we can evaluate the kinetic viscosity at the temperature corresponding to the electric symmetry breaking. If we put that we have some turbulence with some VRMS of the order of 10 to the minus 2, and as you were seeing before, this quantity, this scale here, which would be connected to the anisotropic stresses or to the bubble size, we put it to 0.01, okay, 1%. Then we get an Reynolds numbers, which is 10 of the order of 10 to the 13. So it is absolutely, absolutely huge. And this is why we do expect a turbulence to occur in the early universe. So despite this, turbulence has not been observed yet in early universe simulations, hydrodynamical simulations. And, you know, the reasons are several, but it is not due to the Reynolds numbers, because in general simulation can simulate Reynolds numbers, you know, maybe not of, obviously not of this order, but you know, definitely larger than 1. However, turbulence has been shown to be sustained and present, I mean, sustained, let's say, if it is present in the initial conditions, or if it is induced by some adapted forcing. And for this case in particular of the forcing, I remind you to the work of Alberto Roper-Paul and in general the Nordito group, okay, in which they perform numerical simulation of turbulence, and they see in particular the generation of turbulence inserting some forcing term. Okay, so this is not what we did in this work, as you will see. Now, so what did we do? We have actually first constructed a semi-analytical model of non-relativistic turbulence and of its anisotropic stresses. And the semi-analytical model improves on previous analytical basically exclusively analytical analysis. And in particular, I have in mind, when I say that we are improving, I have in mind this old paper of mine, and together with Ruth Durer and Geraldine Servan, and this paper by Nixa and Gunther Siegel and others. So these two papers were purely analytical, right? Now, in particular, what we improve on the modeling of the turbulence decorrelation, as we will see. And we construct a well-motivated and equal time correlator for the turbulence. And then the real novelty of the work is that we validate our turbulence model with hydrodynamical simulations using the WEPT code, which is the code developed by the Helsinki SASE group, in particular Mark Hindmarsh, David Weir, Kari Rummukainen, and Daniel Cutting. And we indeed, as we will see, insert a turbulent velocity spectrum directly in the initial conditions. Then what we do is that we calculate the gravitational spectrum both from the semi-analytical model and directly from the numerical simulation, and we find a good agreement. So you might ask, but why didn't you just simulate it directly? Well, the thing is that turbulence is pretty much involved, and so we wanted to have a validation, let's say, of the simulation with some our understanding, analytical understanding of the turbulence. And indeed, the fact of having analytical understanding allows us to provide analytical model also for the gravitational spectrum as a function of the turbulence parameter. And this is important because you guys that have your favorite phase transition model, you can actually easily use this result, analytical result, to estimate the signal in your favorite scenario. Okay, so let me start then with the numerical simulations. What does this webbed code do? Basically, it and this is what has been done previously. So it is a simulation of the system, coupled system of the scalar field and the relativistic fluid. So here it is the energy momentum tensor, the full energy momentum tensor, and then you see that there is a coupling term between the field and the fluid, which is due to some friction, that is a friction term that is there to represent the fact that, as I was saying before, the fluid is the scalar field couples to the particles in the early universe. Now, you have here a snapshot of one of these simulations, and it is absolutely obvious that there is no turbulence here, right? So what we see here is that around the bubbles there are some compressional waves that are generated, and that at the collision here there is some perturbation on the spherical bubble shape, but certainly not turbulence. And indeed, so these kind of simulations, this is the first paper here that presented the code, but there has been many afterwards. I'm sure you are all aware. Find that the main source of gravitational waves are indeed sound waves. Now, they also find so that the bubble wall collision is subdominant, so they could evaluate, they can evaluate also the gravitational signals from bubbles, from the scalar field, but the bubble wall collision is subdominant, and in particular, there is no turbulence seen. We believe that the reason is actually that these simulations have been carried on with for pretty weak, let's say, weakly first-order phase transitions, in the sense that the parameter alpha, that in the context of the Planck equation of state is basically the vacuum energy divided by the radiation energy in the universe at the moment of the phase transition, was smaller, sorry, here should be a 0.1 in general for these kind of simulations. And therefore, it means that the typical VRMS velocity, so the root mean square velocity that is involved in the process, is pretty low. And so if one calculates the time of the nonlinearities, this is in general smaller than the Hubble time. Sorry, so again, this equation is wrong. It should be larger than the Hubble time, okay? Much larger than the Hubble time. So one does not expect to see nonlinearities playing a big role in these simulations.
Chiara, can I just quickly ask you, how long do these simulations run? If you say the time is much larger than the Hubble time, how long can you simulate
no. So here, what I'm just saying is that this simulation has been carried out in a setting for which one would not expect nonlinearity to occur, because the values of the parameters is such that the typical time of the nonlinearities is too long. Okay.
Yes, but how much? That's my question basically. By how much is it too long? So you run the simulation for some amount of time?
Yeah, you can't. So the simulation are run in flat space time, so there is no Hubble scale associated to that. Okay, so that this is just a physical statement. You know, that if one sort of interprets the outcome or the setting, but there is no real Hubble scale in the simulation. Now, the one that we do for this work, they typically run, the longest one is for about 70 eddy turnover time. So eddy turnover time would be the same thing, but here you have the VRMS of the velocity. Okay.
I see. Thank you. Okay.
Okay, so I wanted to point out that in this paper, they actually run for a bit larger values here of alpha, and they do see some vorticity appearing, but it doesn't seem to be connected to the formation of shocks. So the dynamics needs still to be clarified. Because in principle, the picture that one expects is that you have first, then, okay, the bubble expansion, first the generation of these sound shells, and then on a short time scale, the sound shell, because the velocity is so high, cause the appearance of shocks in the fluid, and then it is this kind of shocks that then lead to the turbulence. That would be the physical picture one expects. And this has not been observed in this kind of simulations yet. Okay, so what did we do now, just to keep things simple, because we wanted really to follow the entire process analytically. We have performed hydrodynamical simulations of the fluid only. So it means that we have shut down here the scalar field, and therefore the code solves basically the energy conservation and the momentum conservation equations for the fluid, fully relativistic. And we put the turbulence in the initial conditions. So this is the somehow limit, let's say, of our approach is the fact that we don't simulate the formation of the turbulence, but really just we put in the initial condition of the random velocity field with which we initialize the simulation, something, so a configuration which is equivalent to fully developed turbulent spectrum, which we will see in the next slide. With this particular initial condition in which turbulence is already there, we let the simulation evolve. And the simulation then evaluates everything. So the velocity field time evolution, it's an equal time correlator, the stress energy tensor. It then solves the gravitational wave equation and outputs the stochastic background of gravitational waves. Now, let me speed up because I think I have 5 minutes. 10?
Yes, yeah, around 5 minutes. We started a bit later, so maybe 7 minutes, yeah.
Okay. So, and now I will go on to describe the analytical modeling. Okay, so let me see then, let me tell you a bit more about these initial conditions, which are the same for the simulation and for the analytical modeling, obviously. So here you have the power spectrum of the velocity field. You can see that we restrict only to vertical turbulence, and the initial conditions in the simulation are also purely vertical. And this is the shape of the power spectrum of the velocity field. It peaks at a wave number that corresponds to 1 over xi, where this xi, you have already seen it, is in the context of turbulence, the integral scale. So it will be the scale at which most of the kinetic energy is concentrated. And it is again, so we don't properly link it to the previous phase of bubble expansion and sound waves, but it is still something that we expect to be connected to the interbubble distance because the turbulence is produced by the bubble collision as well. And then we have here VRMS, which is the turbulent average velocity. Okay, and both these two quantities, you see, they are a function of time. Why? They are expected to evolve in time because first we imagine that the turbulence is generated, so they grow. And then once the steering stops, what happens is that the turbulence performs a cascade, and it is finally dissipated at very small scales because of the kinetic viscosity. And this, so the energy flows down the cascade and ultimately dissipates the entire turbulent field. Okay, so this process is called free decay of the turbulence. And so it leads to both VRMS and Xi depending on time. Now the shape, particular shape of the power spectrum is such that at small k, so k, wave number smaller than this, the peak, basically, we have a Batchelor spectrum, which arises in the early universe because of a causality argument, and at scales instead larger than the peak, so in what is called the inertial range, we just input a Kolmogorov spectrum, so pretty standard. Okay, and now, so concerning the simulation, this is all in the sense that we put the spectrum and then the simulation does all the rest. But analytically, what we want to do is we want to evaluate this guy, so the gravitational wave power spectrum today. And this is in general given by double time integral. Here is the green function. There is some here this factor due to the expansion of the universe, and the source is this quantity here, which is the unequal time correlator of the anisotropic stresses. So you see here now I take it at different time zeta and time tau. Now, if you assume a Gaussian velocity field, this the anisotropic stress UTC can be connected to the UTC of the velocity field. Okay, and so in the end, it boils down, all our evaluation, it boils down to calculate this double time integral accompanied by this three-dimensional integral on wave number, on wave vector. And the input is really the turbulent velocity field unequal time correlator. Now, we do it first with this assumption, which is based on an old model of the turbulence decorrelation, which is the Kraichner exponential decorrelation, which says that in this in the inertial range, in the inertial range, actually, the velocity decorrelates according to a Gaussian form with a typical characteristic time, which is the Eulerian eddy turnover time. And this is given by 1 over k squared, and then there is a typical decorrelation velocity, which is basically connected to the root mean squared velocity. Okay, so it all seems very simple, but the fact is that we need to extend this Kraichner decorrelation model. First of all, because our velocity field is not stationary, as we have seen, it decays in time during the free decay, so VRMS is not constant in time. And then we need to model the decorrelation also at large scales, so outside the inertial range, in particular in the Batchelor tail. To do that, so we use the theory of positive definite kernels, and in particular we construct a non-stationary Gaussian kernel, okay, that you see here for the unequal time spectral density or unequal time correlator of the velocity field. And here you have this exponential part that remains, okay, inspired by this part, and we have our decorrelation velocity and our time difference. And the fact of using this theory of positive deficit kernel guarantees positivity of this quantity here that you really want to be positive, because this is the energy, gravitational energy density, right? In previous analysis, this was a bit shaky. So this is a clear point of improvement with respect to previous analysis. And then the obvious point of improvement is that we have validated everything with numerical simulation, in particular the decorrelation model. And here you see, so the black line is basically this term here, and the colored line are the outcome of the simulations in the inertial range. And we have also extended the model in the infrared, let's say, at large scales, and it performs not too badly. Besides the, okay, so I speed up. So besides the decorrelation, we also need to model the override time evolution of the turbulent spectrum. Okay, so, and this is usually expected. So VRMS and Xi, the root mean square velocity and the integral scale, are expected to evolve in time with some power laws, because of some scaling arguments that one can perform from the self-similarity or Navier-Stokes equation. And actually, the precise value of these power laws, and in particular of this parameter beta, is extremely debated. So the best thing is to measure it from the simulations, and turns out that what we find is beta equal 3, which is actually coherent with the previous analysis of the Nordita group. So we are happy to agree with what has been found previously also for our simulation, will be this curve here. Okay, and so then we put everything together in this analytical modeling, and we numerically integrate the model, the turbulence model, to get the stochastic background signal. And here you see the final outcome, and you have several lines here. So the orange and the blue one are the simulation results for a given VRMS value. The black one is our semi-analytical evaluation based on the numerical integration of the modeling. And then you have here a green line, which is actually a fully analytical approximation that works pretty well, as you can see. And this is what we will give in the paper and can be used to plot the final outcome of the spectrum. Okay, and now I think I can actually stop here, because this is one extra detail. It's just to tell you that, okay, we have ignored, and in particular in the simulation, we do ignore the period of turbulence formation. But if we include it in some simplified model, you see that the spectra, so this would be the spectra without the turbulence formation, and this would be the spectra with a simple model of turbulence formation. And it actually does matter. So it is extremely important to understand how the turbulence is formed in order to have a definite outcome for the gravitational power spectrum. Okay, so I leave you with my summary here.
Okay, thank you very much for this very interesting and exciting talk, Chiara. We have still time for a couple of questions. So please raise your hand, use the Zoom raise hand tool, and ask your questions to Chiara. Yeah, Marek, please.
So first, maybe a short comment. I think the second time you said you had an error in the equation, I think it was right. Wasn't that just the eddy turnover time, which is shorter than the Hubble time?
Yeah, so it is in our case it is indeed shorter, but okay, now it doesn't want to go back. So I was there talking about the simulations of the sound. Okay, and in the simulation of the sound, it should be the other way around. Otherwise, you would see the nonlinearities. Okay.
Yeah, but that's, so essentially we cut the spectra these days, right? To account for that.
Exactly. Yeah, indeed. And so in principle, instead of cutting a spectra, I mean, if one believes that what comes afterwards is turbulence, you can now plot the green line instead of cutting the spectrum. Well, I mean, I'm not saying that it is the absolute truth, but it is a possibility.
Yes, but does it solve, because I always thought that the problem was the energy budget, that we don't really know how much of the energy stored in
This is still
sound
open. Absolutely, this is still open. So if you see here, for example, there is this, I put here VRMS equals 0.3. So this for us, it is an input value. We don't know how much it is the average kinetic energy in the turbulence. Okay, because this really depends on how it is generated. So for now, what we have done, if you want, is the second bit. So we have provided an evaluation of the signal in terms of this free parameter, which corresponds to the kinetic energy in the turbulence. And then there comes the first bit, which is to connect this value to the bubble expansion and the sound generation, etc. So this is not solved yet.
So one last thing, because you said that the real improvement is this lattice simulation, but if you input the fully developed turbulence spectrum, then how is the new simulation different from the older Nordita group simulations?
So it isn't in the, when they simulate, you know, the situation in which they also have just one input spectrum. The only difference is the fact that we only simulate the vertical part. They have everything inside, right? So in some sense, they have it more realistic because they have the compressional, they have the vertical, and they have the magnetic field. But at the same time, it is difficult in their case to understand exactly what is happening and to generalize the result, right? Because they have very nice spectra, but and some scaling, but it is a bit more difficult to exactly have a clear handle of what is going on. And our point here was to do something simpler, but keeping the analytical understanding of what is going on.
I see. Okay. Thank you. Very interesting.
Okay, I think we have time for one more quick question. David, please.
I don't have a question, so I'll just put my hand down and let someone else.
Okay. Right. So maybe I can ask a quick question on the shape of the gravitational wave spectrum that you showed at the very end. So I remember, for instance, from the first review paper by the LISA Cosmology Working Group, that states an explicit expression for the shape of that spectrum, some analytical expression that depends on two frequencies. One is a peak frequency for this turbulent contribution, and the other frequency is just given by the Hubble scale at the time of gravitational wave generation. So my question is, does your spectrum still have a dependence on the Hubble rate?
No, that's the entire point. So the dependence on the Hubble rate was there because we didn't have a proper modeling of the decorrelation, of the time decorrelation of the turbulence, okay? So we tried to insert as well some sort of Kirkland decorrelation back in the time, but we were finding negative results for the power spectrum. Okay, and this was because we didn't model it as a proper non-stationary kernel. So in the end, what we did, we argued, okay, let's try to model the decorrelation directly in the anisotropic stresses, and we model this top hat scenario for the decorrelation of the anisotropic stresses. And this provides, as a characteristic time of the generation, basically 1/k, okay, 1 over the wave number, which is not too wrong, but it did also provide this kink at the Hubble scale, at the inverse of the Hubble scale in the spectrum. And we actually now found out that this kink, it was an artifact of the top hat decorrelation. And what we have done now is much more precise, or much more true, let's say, according to the turbulence theory.
I see. Okay, that's very interesting. Okay, thank you. I think we have to stop here and then move on. We are past time already by a couple of minutes. So thank you very much, Chiara. And now let's move on to the next talk by Jessica. Hi, Jessica.
Hi, Kai. Shall I share my screen?
Can you start sharing your screen?
Yeah.
Perfect. Okay.
Okay.
Right here. It's full screen. We can see your mouse cursor. I think that's all fine. So then, yeah, without any further ado, let's continue with the second talk of this session. The format is 20 minutes plus 5 minutes for questions. And yeah, so we will hear from Jessica Turner from Durham University about computations of the electric weak bubble wall velocity. Please, Jessica, the stage is yours.
Okay, before I begin, I'd like to thank the organisers. I'm very pleased to give this talk here today. I will say that there are a lot of details I'm going to skim over because this is a 20-minute talk. However, if you've got questions at the end, there are plenty of backup slides. All right, so as Chiara beautifully reviewed, we know that a first-order electroweak phase transition is not predicted by the standard model. However, minimal new physics can create a first-order electroweak phase transition, and there's a lot of associated rich physics, such as the creation of the matter-antimatter asymmetry via electroweak baryogenesis, the creation of topological defects, which was discussed yesterday, primordial magnetic fields, and also importantly, which is the topic of today's work, the creation of a stochastic gravitational wave background. So essentially, well, this will probably be covered in detail by my fellow speakers, but I'll very briefly say why the electroweak bubble wall velocity is important for gravitational waves. Essentially, gravitational waves can be sourced from different contributions, either from the contributions of the bubble's walls colliding, the sound waves, the turbulence, or the magneto-hydrodynamical effects within the early universe plasma. Depending on how quickly the bubble walls are traveling, these different contributions are more or less important. Therefore, precise determination of the electroweak bubble wall velocity is important for essentially determination of the gravitational wave spectrum from these first order electroweak phase transitions. Secondly, if a first order electroweak phase transition created the matter-antimatter asymmetry via electroweak baryogenesis, then the wall velocity is important for that calculation. It had been thought that the faster the walls move, the less efficient electroweak baryogenesis was. However, this has been shown not to be the case rather recently by Klein and Kainulainen along with Dorsch and collaborators. So in the remainder of this talk, what I'm going to discuss are relativistic bubble wall calculations. So the following calculations I'll discuss are not relevant for subsonic bubble walls, and you need to use alternate methods of calculating the wall velocity. So what do we really mean by the bubble wall velocity, and how does that arise? So when these bubbles nucleate, percolate and expand in the early universe, their expansion is driven by the vacuum pressure, which results from the symmetry breaking Higgs potential. Of course, this is independent of the Lorentz factor of how fast those walls are moving. However, this is a Higgs bubble moving in space. The Higgs condensate couples to the early universe standard model plasma, and therefore there will be a resultant friction of the particles as they interact with the bubble wall. This frictional force, which retards the driving force given by the symmetry breaking Higgs potential, is non-trivially dependent upon the Lorentz factor of the wall, as we're going to see. The terminal velocity, which, as we said, will determine the gravitational wave spectrum, is found by a result of balancing these two forces, i.e. the force which drives the expansion, which we determine from the Higgs potential, and the force that retards it, which will be the subject of this talk. So before I begin, I'd like to just very briefly review kinematics, which will be very important, and several assumptions. So when we nucleate these bubbles in the early universe plasma, they inherently break Z translation invariance if we say that they're moving in the Z direction. So we know from Noether's theorem that the longitudinal momentum or momentum in the Z direction is not conserved. So how do we write down these longitudinal momentum components of particles entering the bubble wall as shown on the right here? Well, we write them down simply in terms of the energy squared minus the transverse momentum squared minus the mass in the symmetric or broken phase. And that gives the longitudinal momentum in the symmetric or broken phase of the given plasma. So S and H simply denote symmetric or broken phase. In the remainder of this talk, I'm going to review one-to-one calculations, which will become clear shortly, one-to-two calculations and one-to-n calculations. And throughout all of this, I'll be assuming that the bubble walls are infinitely thin. So as I said, the bubble wall inherently breaks Z translation invariance. However, transverse momentum is conserved across the wall. Therefore, particles entering, if it's a one-to-one interaction of particle A transforming into particle B and gaining a mass inside the bubble, then the transverse momentum is equal on either side of the bubble wall interface. Likewise, energy is also conserved. Okay, so now we're going to review the one-to-one relativistic bubble wall calculations, which were pioneered by Peter Arnold and Bodeker and Moore back in 2009. So all we're going to do is heuristically derive what is the friction on the bubble wall if the bubble walls are moving relativistically, and what's the friction imparted from particle A gaining a mass as it enters the wall and becoming particle B. So the change in momentum imparted from these incoming particles to the wall is simply the change in longitudinal momentum as defined on the previous slide. And if we're in the regime where the bubble wall is relativistic, then in the rest frame of the bubble wall, the particles are coming very fast and their energy is extremely large. So EA and EB are very, very large relative to their masses and their transverse momentum. We can make a Taylor expansion, and what we find is that the impartation of momentum from these particles to the wall is simply the mass squared difference of these particles, B and A, divided by their energy, which goes like gamma T. Therefore, the pressure from this one-to-one interaction is simply the force over the area, which is the change in momentum over the area times the time. And that is simply given by gamma T cubed, because the flux of the incoming particles is Lorentz contracted in the Z direction times by the change in momentum, which just goes like delta M squared over 2 gamma T. So what you see is that the Lorentz factor of the wall cancels here, and the pressure from this one-to-one calculation simply goes like the change in the mass times the temperature of the ambient plasma over 2. We can formalize this rather heuristic derivation in terms of a differential probability for A to transition to B, A observable, which is the momentum transfer, multiplied by some quantum statistical factors, which tell you the nature of particle A and particle B. And of course, we need to sum over all species of incoming particles. This is the flux here. So what exactly is this differential probability? How is it composed? Well, it's composed simply of the phase space of particle B, which I remind you is the particle inside the bubble wall that's penetrated it, multiplied by 3 delta functions. So there's 2 delta functions associated with the transverse momentum, 1 associated with the energy. In normal quantum field theory, where you don't have a bubble that's breaking Z translation invariance, you'd have a 4th delta function, but that's not the case because we've got the bubble wall here. And this delta AB is just to enforce the fact that we're not considering flavor change across the wall. So we're having a quark of a given flavor penetrate the bubble wall because it's extremely energetic and it remains the same flavor while gaining a mass. So we can take this differential probability, combine it with the momentum transfer, the quantum statistical factors, and the flux. And what we find again is that the pressure for these one-to-one interactions go like gamma naught T squared delta M squared. 8 years after this original calculation by Bodeker and Moore, they studied a 1-to-2 interaction. So here they have particles coming into the bubble wall. So this particle has momentum PA, it's on its mass shell, the bubble's moving to the left. It interacts with the bubble wall. Through this interaction, it's put off of its mass shell. It can create some soft quanta PC, and there'll be a particle PB, which is hard or energetic. And the idea here is that the incident particle's energy can be very efficiently converted into the mass of a second particle, let's say PC, which may be a massive gauge boson such as a Z or a W, and transverse momentum, which must be balanced by the particle with momentum PB. And the idea here is that the momentum exchange with the wall is much larger precisely because you've created a massive particle and you've redistributed the transverse momentum. Naturally, if this particle PC has zero transverse momentum and zero mass, you recover the one-to-one calculation. So we can go back to the master formula, which was simply the differential probability multiplied by the quantum statistical factors times the observable, which is the momentum transfer from the incoming particles to the wall integrated over the flux. We integrate over the phase space of particle B, which is this hard particle for the rest of the talk. And what we find is the pressure for a 1-to-2 interaction has the following form. So here we have a matrix element squared times by some combination of phase space from integrating over B and that observable. So I should say that the matrix element in the original 1-to-1 calculation was 1. This was because the assumption was that all the particles coming into the bubble have very, very large energy, and therefore they can penetrate the bubble and interact with the wall. In any case, for this expression for the 1-to-2 pressure, Bodecker and Moore are particularly interested in the following kinematic regime. Firstly, they find that the pressure is enhanced when the transverse momentum of the soft emission given by PC is low, and the longitudinal momentum is also small relative to gamma T, and particle with momentum B is essentially hard, and the incoming particle is on shell and also very, very hard. So we can take this combination of the observable combined with the phase space and rewrite it in terms of two small parameters which encapsulate how collinear emission C is and how soft it is. So if it's very collinear, then C lies along B, and if it's soft, it has very, very low energy relative to the incoming energy of the hard particle. So we want to be able to rewrite PC ZS, which is just the longitudinal momentum of particle C in the symmetric phase in terms of this small parameter epsilon. So we just do a Taylor expansion, and we can write this longitudinal momentum in terms of energy 1 minus a small parameter encapsulating the collinearity of the soft emission. And then we will also want to rewrite PBZS in terms of the soft parameter. So again, we just take the longitudinal momentum of B, which I remind you for this example is a hard fermion inside the bubble, and you can rewrite it in terms of the energy and 1 minus x. We can substitute these expressions in this yellow box here, and what we find is the observable times the phase space factor is simply the transverse mass of particle C divided by its energy. So now we've massaged this master formula for the 1-to-2 pressure into the following rather simple form. However, we still have the matrix element squared to determine. So Bodecker and Moore calculate the matrix element by convoluting mode functions, which are treated using the WKB approximation with a vertex function. So I remind you, these mode functions come from solving the equation of motion for a particle in an inhomogeneous background. That's what, and essentially we have a phase here, which is dependent upon the longitudinal momentum, which changes because there's that wall there, and then there's an amplitude. And they approximate this amplitude to be close to 1, and that essentially tells you that all the incoming particles are transmitted into the bubble. So these mode functions come from the equation of motion in an inhomogeneous background, and the vertex function is sensitive to the nature of the interaction. So for instance, was this an incoming fermion splitting to a scalar fermion, or was it an incoming fermion splitting to a gauge boson and a fermion? Okay. So how does one actually calculate this matrix element? Well, because we have these mode functions, we need to integrate over the z direction. And we define z of minus infinity to be infinitely far in front of the bubble wall. At the wall, which again, as I stated, we're assuming has infinitely thin width, z is equal to 0, and then we can integrate from z equals 0 up to infinity. And we integrate over these mode functions, and what one finds is that the matrix element has the following rather simple form. So it looks like VH over AH minus VS over AS, where again, these vertex functions, as we're going to see, tell you the nature of the interaction, and the AS's and AH's tell you the fact that the wave functions of the particles inside and outside the bubble differ. I should say these AHs and AHs, the AH and AS actually very much resemble propagators, but they're actually only propagating in the Z direction, which is somewhat unsurprising given that the bubble breaks Z translation invariance. Okay, so what they find is the matrix element squared has the following form. They factored out this V squared, and what they have remaining is this combination of AHs and ASs from the mode functions. So as there's not a great deal of time, I'll just say that these vertex functions are related to the Altairelli-Parisi splitting functions. And essentially what happens is they tell you that in the regime where the emission is soft or where X is small, the matrix element becomes enhanced. And this is something rather universal. Matrix elements become enhanced in the soft and collinear regime. Okay, so now we've derived where these mode functions come from and integrated them, and we've discussed what the vertex function is. We're going to combine those. So combining the previous form of the AS's and AH's, we find that that's proportional to the mass change of the emission across the wall. And then we still have our vertex function divided by our factor X. So if we take the vertex function to be, for instance, a fermion emitting a transverse gauge boson and going on to a fermion, we find that it's proportional to PC transpose, so the transpose momentum of soft particle C divided by X all squared, but there was an X squared coming from this phase space factor that gets cancelled. And the reason I'm tracking this cancellation of X is because X is small, and if we didn't have this cancellation, then the matrix element would be suppressed. And that's why, at least in the Bodecker and Moore case, they find that it's the emission of soft gauge bosons that enhances their matrix element. But of course, we need to combine this matrix element squared with the observable or the momentum transfer, which we derived earlier, and we find this form proportional to the Casimir, the energy. It's inversely proportional to X, which again is small, and it's sensitive to the mass of the emission. So Bodecker and Moore then integrate this over the phase space of particle C, and they cut off the integrations at the masses. They cut off the integrations of the energy and the transverse momentum of the mass. Doing so, what they find is that the pressure scales in the following way. We get an m to the fourth coming from the mode functions. This m here comes from integrating AS and AH over Z. We have 1 on m coming from the integration of the energy of particle C. We have 1 on m squared coming from the transverse momentum integration. And then we have our Lorentz contracted flux of incoming particles. So once you just cancel these off, what they find is that the pressure goes like m gamma t cubed. Of course, since the vacuum pressure does not grow in gamma, but the frictional pressure does grow in gamma, a terminal velocity will be reached. Another salient fact about their pressure is that it's proportional to the mass. So as the phase change goes to 0, their pressure goes to 0. That is to say that if there's no interactions, or if any of the particles of A, B, or C do not change mass across the bubble wall, the pressure will be 0, as one would expect. Importantly, the matrix element was derived using a convolution of WKB approximations and a vertex function. And the integration of their soft emission was cut off by the mass of the gauge bosons. So this is a very, very interesting paper, and to myself and my collaborators, it almost looked a little bit like a scattering experiment, such as deep inelastic scattering, where you have a very, very energetic incoming particle probing an object, namely the bubble wall, and scattering. And there are not so many scales in the problem. And if this, well, suffice to say, if the center of mass energy, it will be very large since gamma T is very, very large. And if the incoming particle can probe the wall at these very high energies, one might suspect there may be many soft emissions. So this is what I'm going to discuss in the next
5 minutes. Yeah, if you could.
5 minutes.
Yeah. Okay.
Okay, 5 minutes. So my collaborators and I were very interested in looking at how the pressure would scale if we had many, many emissions. And this is largely inspired by the calculation of Bodecker and Moore. We looked at the one-to-one calculation, and we're going to treat this as a leading order interaction where we have an on-shell particle called A. It probes the wall, imparts some momentum, and scatters off the wall. As we saw, what they found is that the 1-to-2 interaction imparts much more pressure than the one-to-one interaction, precisely because it's through this act of probing the wall, you put this incoming particle off its mass shell and it can emit a second particle. So the logic is, if 1-to-2 is more important than 1-to-1, is 1-to-n more important than 1-to-2, given the fact that perhaps this outgoing particle can have large virtuality and produce many soft quanta in the final state. So given the paucity of time, I'll be very, very quick with this. Essentially, our calculation is very similar to Bodecker and Moore, but it deviates in one particular way. Our ASs and our AHs are not derived from the WKB approximation. Instead, we enforce gauge invariance of our matrix elements squared, and these ASs and AHs are covariant propagators. As such, they are actually inner products of PAS and PCS and PBH and PCH. I should say that in the limit, the emission is soft and collinear. They have the identical form to the Bodecker and Moore ASs and AHs. However, outside of the soft limit, they can differ. As I briefly mentioned, we were motivated to do this redefinition in order to treat these essentially propagators covariantly. So VS and VH, as I had said, they allude to the nature of the emission, and we're treating them as different processes. And we can't really ask what, if one process happened or another process happened. They both have, there's a kind of quantum mechanical process, they both have occurred. So VS essentially means that we have on-shell particle PA, it emits a soft quanta, and it's put off of its mass shell, and it essentially transfers momentum to the wall, which is indicated in this blue dashed line, which will then put PBS on its mass shell. And it's this intermediate state which we interpret as a fully covariant propagator, and that is our AS. Likewise, AH is the analogous process, but this time the propagator is inside of the bubble, which is denoted by this blue dashed line. In any case, our matrix element has the following form. This is a gauge invariant matrix element squared that corresponds physically to essentially a charged particle decelerating, and when it decelerates, its radiation field reconfigures and it produces soft quanta. Okay, so given this matrix element squared, we can study the process where we have a particle PA interacting with the wall, emitting a massless particle PC, so for instance, a photon or a gluon, and PA acquires a mass inside the wall. So there is a phase change. However, we're particularly concentrating on the process where PC is massless. As there's not very much time, I can always allude to that if someone asks the question why this is the interaction we're particularly interested in. Nonetheless, given the prior matrix element squared, we can look in the regime of small kt or large kt, and what we find is that we get large logs, which necessitates a recimation. We perform this recimation analytically using very standardized techniques applied in collider physics, and we also perform this recimation numerically. Given the time, and that's my 5 minutes, suffice to say, the average momentum transfer we find from these many soft emissions goes like gamma T. And therefore, the pressure will scale like gamma squared T to the fourth. Sorry, I'm a little bit over time. So I'm just going to say that we do need a phase change. Otherwise, the leading order interaction, which for us is the one-to-one, is 0. what we've done is we've calculated in all orders pressure in a gauge invariant manner. And what we find is that the pressure scales like gamma squared. Naturally, we need a phase change. However, this can come from the hard fermionic leg and not from the soft emissions. Suffice to say, there are really lots of interesting issues to explore and assumptions we've made that we want to move beyond. And I thank you for your time and apologize for going over time somewhat.
Thank you very much, Jessica, and no worries. Yeah, I have to apologize for rushing you a bit towards the end, but thank you very much for this very interesting talk. Do we have questions for Jessica? Please put up your hand, raise your hand, and speak up. There is some discussion going on in the chat, but oh yeah, Alex, you want to comment?
Hey, so just a small comment that I think there is paper which disagrees on gamma squared pressure.
Yeah, there's a lot of discussion.
And in particular, I think it's not gamma squared against gamma. It's more like whether you have pressure which scales as alpha QCD, which I think, yeah, so this I think is the main disagreement.
Yeah, there's a lot of there's disagreement in the community, and of course this remains to be explored. As I said, there are lots and lots of issues to be explored.
And I would say the main disagreement is whether there is alpha QCD gamma square pressure or not. Okay, that's it. Thank you.
Okay, thank you very much for this comment. Do we have another question for Jessica? Yes, please, Bogomila.
So if you were to name one of the assumptions that you would expect could change something in your results, which one would that be? So is there a point, like what would be the first point you would like to reconsider? Sorry.
So sorry, my internet appears to be unstable. So what we would like to revisit is moving beyond the infinitely thin wall width, because essentially for us, we treated the one-to-one interaction as a leading order interaction. And what happens is that, at least in our approach using the Viv insertion approximation, essentially any particle which can gain a mass across the bubble wall will interact with the bubble wall and be put off its mass shell. How deeply it probes the bubble wall or the amount of momentum exchange for us can be as large as gamma t. And we believe this comes from the fact we've approximated the wall to be infinitely thin. So in an analogy with, I very briefly made an analogy with deep inelastic scattering. So if the interaction with the wall at leading order is given by the hard function, we can have an analog of that with a form factor. And so if we change the width of the bubble wall, that will probably change the final result, and that's something we're investigating.
Okay, thanks a lot.
Okay, I don't see any further questions, and I think it's also time to move on. So thank you very much again, Jessica. And then let's move on to the next talk in the session by Carlos. Carlos, are you around?
I'm around. Can you hear me appropriately?
Yes, yeah, perfect. We hear you perfectly. And can you also start sharing your screen?
Very good.
Okay, that looks great. So then, yeah, without any further ado, the next talk is by Carlos Tamarit from TU Munich. And then Carlos is going to tell us about bubble friction in local equilibrium. Please, Carlos.
All right. Thank you to the audience for being here, attending this talk. And especially thanks to the organizers for inviting me and giving me the opportunity to talk about this work about bubble friction in local equilibrium, which was done in collaboration with Shyam Balaji at the University of Sydney and Michael Szpanowski at Durham. So what is the aim? The aim is to focus on bubble friction in local equilibrium and provide new understanding in relation to previous literature and some novel explicit calculations. Why is the content of a paper new in some ways? Because we relate previous results in the literature. Argue that they are looking at the same effect. And we provide novel understanding in simple terms of entropy conservation. And also, we confirm directly this friction effect in local equilibrium by studying time-dependent solutions and identify the local friction of the source as coming from the field dependence of the enthalpy. And we also illustrate this effect not just for deflagrations, but for detonations. And the plan of the talk is to review the usual understanding of bubble friction, and then move on to friction in local equilibrium, surveying the previous literature, then reviewing or obtaining the equations for bubble expansion in local equilibrium, just starting from stress energy conservation, and then go on to numerical studies. So let's review the usual understanding of bubble friction. Okay, the bubble basics, as we have seen in a first order phase transition, at some temperature, nucleation temperature T nuke, there's in the middle of a symmetric phase with no expectation value of a scalar field, the bubbles with break the symmetry start forming, and due to the difference in potential energy, there's a driving force that makes the bubbles in principle accelerate, but friction effects could give it a finite wall velocity. There's two main types of expansions. One is deflagration, which is when the bubble wall has a speed which is less than the speed of sound in the plasma. And what happens is that the bubble pushes the fluid in front, which acquires some non-zero velocity. And there's another mode, which is a detonation, in which the bubble wall moves with a speed greater than the sound of speed in the plasma, and then it can only perturb the field in the wake. And okay, this is just a simplification because there's also hybrid solutions, but for the purpose of a talk, we just have these two.
Carlos, we don't see your slides anymore.
Okay, I don't know what happened. Is it back? Yeah. All right. Okay, so as we have seen in the previous fantastic talks, without friction effects, latent heat will just convert to bulk motion, and the bubbles are expected to accelerate towards luminal speeds, which is called runaway bubbles. And as we have also seen, colliding bubbles cause gravitational waves, and in principle, there's the contribution from the anisotropy sourced by the scalar field profiles in the bubbles will be called so-called the envelope contribution to gravitational waves will be larger the larger the speed of the bubbles. But also, as Jessica reviewed, the Higgs bubbles could lead to electroweak baryogenesis, usually requiring low speeds, although recent results in the last year also suggest that it could work for higher speeds. But in any case, it's crucial to understand friction to understand possible sources of gravitational waves or the viability of electroweak baryogenesis. How is friction usually accounted for in the scalar equation of motion? Well, Prokopetch and Moore in 1995, they just started with the equation of motion of scalar fields averaged in the plasma, and they obtained the usual vacuum piece and then a new piece involving the distribution functions of particles. Now, if you expand these distribution functions as an equilibrium piece plus a deviation from equilibrium, it turns out that the equilibrium piece is exactly nothing more than the finite temperature correction to the effective potential. And then you get an extra non-equilibrium piece. And this just would look like the ordinary equation of motion at finite temperature, which would in principle show no friction. And then this is interpreted as a friction term coming from deviations of equilibrium. How does one get a friction from this local equation of motion, a friction force per unit area? I start with the local equation of motion. I'm in the wall frame, assuming static expansion that a stationary regime is achieved. And then I multiply by phi prime and integrate over z. And then the first term is a total derivative, 1/2 the derivative of 1/2 phi prime square. And then by integrating, I only get boundary pieces, but away from the wall, the derivatives of the field are 0. And then the integral of this piece is essentially the integral of v d phi times d phi. So I get just the change in potential. And then I get a contribution from the rest. And then this can be interpreted as a balance of forces. This is the driving force, as was seen in the previous talk, coming from the change of potential energies between the two phases. And this will be the friction force per unit area, as shown by Bodecker-Moore coming out of equilibrium. And to make connection with Jessica's talk, in which you can get an alternative expression of this friction force by going back a bit, assuming simply that there's an ultrarelativistic wall so that all particles get transmitted, and then you don't have to worry about details of the integration of F. And then it can be seen that you end up with a balance of forces looking like this, which is the vacuum driving force, and then total force from the plasma, including friction, which involves this delta Pz that we saw in Jessica's talk. But it would seem then that for a constant velocity for temperatures below the critical temperature can only be achieved from out of equilibrium effects. And as we've seen at leading order, the friction is velocity independent, allowing for runaways, but then higher order effects such as what Bodecker-Moore did earlier and what Jessica and collaborators have done imply that one can get still some velocity dependent friction. So it's commonly assumed that there's no friction in local equilibrium, but then why am I talking here? And this is the next part of the talk, review what previous literature has done versus in regards to local equilibrium. So as we saw in the talk by Chiara, it's instead of talking about distribution functions and all the complicated treatment, one can have a phenomenological friction term given with a friction coefficient. And already in '93, Ignatius et al. Did some studies of deflagration by solving a couple, the equation of the field plus the equations in the plasma. And they have this plot in which they have this gamma, which is essentially the inverse of this friction. So friction is 0 for large gamma. And you can see that one seems to achieve wall velocities which are less than the speed of light. Also in 2010, Espinosa and collaborators like Jose Miguel No, who I think is in the audience, did studies, and then it was, it turns out that when the friction is low, they still get, these contour lines are contour lines of wall velocities, and they still get subluminal speeds. But it was not realized that maybe, is there a contradiction that there's a friction-like behavior? It was only known constant in 2010 that really consider this and were the first to talk about a friction-like effect in local equilibrium. And they showed that these subluminal velocities were a result of hydrodynamic obstruction that causes the fluid to heat up in front of the bubbles, and then this reduces the potential energy difference between the phases and the driving force. And the effect was thought to happen only in deflagrations. Now, more recently, Barroso-Mancha, Prokopec, and Zvizdevska, who is one of the organizers of the conference, just had a very elegant derivation of some of this friction force in local equilibrium. So they just start with the stress energy momentum tensor of the plasma, assuming Lorentz invariance, which involves rho plus p, the density and the pressure, which this combination is the enthalpy, which is itself related is T times the entropy density. And then away from the bubble wall, the stress energy momentum of the scalar field receives no contributions from gradients because the field stabilizes. And then just by imposing conservation of the ZZ component of the total stress energy across the plasma, you get this equation. First, you get a contribution from the potential here and from the pressure here. So this is the left-hand side. And then you get a contribution from TS and then ZZ component of U, which is gamma square V square, but gamma square V square is gamma square minus 1. And then you have T delta S if you assume that velocity and temperature are constant across the wall. So then you interpret this as the driving force, and this balanced by a friction force, even though you are in equilibrium. And in this derivation, there's no distinction between detonations and deflagrations. And then the friction grows with velocity due to this gamma square. And the interesting point made in this paper is that, okay, you always will have some degrees of freedom in local equilibrium that will give some additional friction-like behavior. What are the open questions? Well, I mean, the hydrodynamic obstruction of Constantin and No, is it the same as this friction force of Barroso-Mancha? Because both deal with some effect at equilibrium. But okay, this latter friction force should apply regardless of whether you are in a detonation or deflagration, while the effect of Constantin No was thought only to happen for deflagrations. Moreover, this friction force is examining by looking at the stress energy far away from the wall, but where is the friction encoded at the differential equations for the scalar and the plasma. So I go to the next part of the talk, which is considering the differential equations for the expansion of the bubbles just out of imposing stress energy conservation at the local level. So again, I have my stress energy tensor, which has a contribution from the scalar field and a contribution from the plasma, again, in terms of this density and pressure, which I relate to the enthalpy omega. And then I just impose local conservation of stress energy. And then I will, I have a free index, and then I will have some contributions which go as derivative nu of phi, and being phi could be in principle be arbitrary. So I have to separately cancel the pieces that are proportional to partial nu phi, and I get an equation of motion for the scalar field. And this pressure is nothing, as we will see, but the finite temperature corrections to the effective potential. So I get the naively expected equation of motion for the scalar field at finite temperature with a finite effective potential. And then I get these equations for the plasma, and which were these equations in a less simple notation, but have been obtained before by Ignatius and collaborators. And what we are now trying to explain is that the friction-like behavior at the level of these local equation of motions comes actually from the field dependence of this enthalpy. Okay, and then, okay, so how to solve this equation? So we have the pressure and the enthalpy. And the point I want to make now is that everything can be computed from the standard finite temperature corrections to the effective potential. The reason is that when I assume local equilibrium, the pressure is related to the free energy density, which itself is connected to the finite temperature corrections to the effective potential. So P is minus the delta T coming, the contribution to the potential energy coming from thermal effects. And this is calculable in an arbitrary model from finite T effect field theory. Moreover, if I need to compute the enthalpy, which appears here in the equations, I just can use standard thermodynamical identities. And it's actually that relate the enthalpy to the derivative of the pressure with respect to the temperature, which then I just connect to taking derivatives of the standard effective potential with respect to the temperature. And if I don't assume local equilibrium, one can still compute things like the entropy from computing in field theory correlators of the stress energy momentum tensor. And this has been done in beautiful calculation by Barroso-Mancha and collaborators. And the results match in local equilibrium these thermodynamical identities. So the next point is that these equations for the plasma actually imply conservation of total entropy. So I multiply, contract with U nu, and then using these identities from the previous page, you can easily say that there's some divergence, some conservation law from some entropy current. Now I integrate this over a space volume, and then I get the temporal derivative of some total entropy, which is just the integral of the entropy density times our gamma factor. And then I would get a piece proportional to the spatial divergence, but then I use the divergence theorem. Then this is a boundary term, but I assume the fluid is arrested in the boundary, and then it doesn't contribute. So I get entropy is conserved. Okay, what is the entropy density in a plasma is dominated by the relativistic degrees of freedom and is parameterized by the effective number of relativistic degrees of freedom. And a phase transition makes some degrees of freedom heavy. So this implies a local decrease in entropy density. But if the total entropy is conserved, there has to be a heating effect somewhere else in the plasma to compensate. And this explains why there has to be this heating effect that was first pointed out by Konstantin and No. But it should also not just apply to deflagrations, but also to detonations. One can go now to a planar wall frame, assuming that one reaches a stationary regime, and one has the scalar equation of motion and two equations from the ZZ and 0Z components of the stress energy momentum. I assume a bubble propagating in the Z direction with planar symmetry and going from left to right. But now from this second equation, actually, well, these equations were solved actually by Konstantin and No. And the point I want to make now is that from this second equation, just by comparing two different points away from the plasma, I actually get exactly the friction force of Barroso-Mancha, Prokopec, and Rzhizewska. This means that the effect that was looked by Konstantin and No is exactly the same as Barroso-Mancha et al. Were looking at. And just a technical point, I can reduce these equations to a single scalar equation, because here, if I have, I can, in principle, use these two equations to solve for the temperature and velocity as a function of phi and phi prime. And I can parameterize, trade these two constants by, let's say, the fluid in front, away in front of the bubble wall, and the temperature far in front of the bubble wall. And then I get a single equation for the scalar field, but I have some special indirect dependence on field derivatives here. So one can understand that in principle, there can be a friction-like behavior because of this dependence on derivatives. The boundary conditions are, of course, that in the symmetric phase, which I assume is for z going to infinity, the field goes to 0, and then the field derivatives have to go to 0. And additionally, I expect that in the broken phase, the field should go to a minimum, and then there's an additional boundary condition that the second derivative has to vanish. Okay, so in principle, the boundary conditions in the first line, if I choose values of v and t, I can always do a shooting method and find a solution. And it's only when I apply the second condition that it will fix, for example, the parameter v plus in terms of t plus. And then I have one free parameter, but I can, of course, now fix it by relating it to the nucleation temperature. In the case of deflagrations, I still have to consider the deflagration profile in front of the bubble wall, but this is just a small complication. And then let's move on to our numerical studies. So first, okay, we consider a simple example model, which is a standard model extension by n additional complex singlets, allowing for a first order phase transition for the Higgs. I have just the Higgs and then a family of X scalars with Portal couplings with Higgs. And the pressure, I just obtain it from thermal corrections to the effective potential, which are standard, and I just, for simplicity, use a high T expansion. So I have the vacuum piece going as the usual T to the fourth, and then I have field-dependent contributions. Now I study the time-dependent solutions, just putting as an initial condition a perturbed critical bubble. And first, here I have the bubble wall as a function of time, the bubble wall velocity as a function of time. First, if I ignore the derivatives in the scalar equation, in the equations for the plasma, if I ignore the derivative with respect to the field, I get a runaway behavior. But if I account for the derivatives of the entropy with respect to the field, I really get lower velocities, and there's indeed a friction-like behavior. And the solutions, well, look at this. This is the profile versus R. We assume here radial symmetry for different times, and you see an expansion with what looks like constant velocity. And then we see, there's deflagration, there's perturbation velocity building in front of the wall, and also the fluid is heating up in front of the wall. Now, this was a time-dependent phenomena where still we didn't simulate enough to get the steady state. I can look at the steady state directly by solving these equations in the wall frame. And then we have, without imposing the condition of second derivative going to 0, there is a family of solutions. And here I've plotted the bubble wall velocity as a function of the temperature just in the deflagration front in front of the wall, immediately in front of the wall. And you can see that despite being in local equilibriums, one gets subluminal speeds. And now I can compute the back reaction force, and as a function of the wall velocity. And in the dashed line is the expression assuming that the velocity and temperature are constant across the wall, and in darker blue is the expression without this assumption, so it's more exact. And we see, okay, the approximation is reasonably good, but the point is that in both cases the friction grows with velocity, as expected from the arguments of Barroso-Mancha et al. How does the solution look like? Okay, so near the wall I have this static solution in which the temperature as a function of z just this is the bubble wall, and here I have this heating effect above the critical temperature, and then the velocity field is also perturbed. And then, okay, in order to match it with nucleation temperature away from the wall, I have to link this to a hydrodynamic profile, which can be done. But okay, this was for deflagrations, but for detonations, which were in principle thought by Konstantin No, it was not clear whether this heating effect would be there. We have found solutions, and then the point is that this, yes?
5 minutes.
Yeah, thank you. we have found that these solutions to the temperature as a function of phi and phi prime and the velocity as a function of phi and phi prime are actually multi-valued. And so is this pseudo potential V hat that appears in when I reduce the problem of a single scalar equation. And it turns out that one of these branches actually supports static solutions for detonations. And we have computed one example of these solutions, and we have found that the friction force deviates from the formula in the paper of Barroso-Mancha et al., which assumes constant velocity and temperature across the bubble wall by a factor of 3. So this means that in detonations, when the speed gets large enough, you have to be careful with the temperature and velocity variation across the wall. And what does these solutions look like? So now is a detonation. So I put the fluid disperser behind the wall. So this is the hydrodynamic profile on the left behind the wall, and the static solution near the wall is on the right. And we see that the temperature is heated behind the wall, and it reaches a critical temperature above the critical temperature. And you might be puzzled because, behind the wall, I'm supposed to be in a broken phase. How can I have a temperature above the critical temperature? And the answer is that I can have a temperature above the critical temperature, but still a metastable, non-trivial vacuum. And what is happening in these solutions is that immediately behind the wall, the scalar field is excited into a metastable vacuum. And then in the hydrodynamic profile behind the wall, then the temperature relaxes back to the nucleation temperature. And then I get the usual stable vacuum. And I can also find a solution that matches the profile for the velocity in front of, behind the bubble with a hydrodynamic solution below. And with this, I can arrive to my conclusions, which is that even in local equilibrium, there's a non-dissipative friction-like back reaction effect. And this effect is what was observed by Konstantin and No in 2010. And this is the same as what's proposed recently by Barroso-Mancha and collaborators. And we have provided an intuitive understanding based on entropy conservation, just that this heating effect is just imposed by conservation of total entropy, because the phase transition front decreases the entropy density in the broken phase. And also, we have clarified that the local, the effect of friction is implemented locally by the field derivatives of the enthalpy. And we have also showed that, as expected from the results of Barroso-Mancha and collaborators, the back reaction exists also for detonations. Although in this case, when estimating the friction force, changes of temperature and velocity across the bubble should be tracked. And with this, I will finish, and thank you for your attention.
Yeah, thank you very much, Carlos, for this very interesting talk. We have time for a couple of questions. So please raise your hand and speak up. Ask your question to Carlos. All right. No questions? I was actually wondering, maybe that's an academic question and it doesn't really apply to realistic scenarios, but I was wondering what would happen to your analysis if you perturb this by chemical potentials?
Well, you would have addition. You would have addition, and you could model them by an additional contribution from out of equilibrium. Mm-hmm. And then I would assume that there's just, in a generic case, you have some degrees of freedom in equilibrium, in which we have this back reaction force. And then you would have additional degrees, which are out of equilibrium. And then you would have the usual friction force. And naively, one would think that in principle, both friction effects should combine and give smaller velocities. But this, I don't think there are yet dedicated studies which try to combine both effects.
Right. Okay. I see there's a question by Mark.
Yes.
Mark, please unmute yourself.
Yeah. Thanks. Thanks for the clear talk.
Thank you.
I must admit, I'm extremely puzzled by this paper by Barroso-Mancha et al. Mm-hmm. Because they appear to be using energy conservation across the wall twice, in the sense that matching TZZ and T0Z across the wall is part of the construction whereby one matches the boundary conditions for velocity and enthalpy, and you can kind of do that for any velocity and any enthalpy. I mean, so I'm used to the fact that for a particular potential, you may not be able to interpolate between the two, and you found some examples of that case. But certainly calling the change in pressure and potential, and then matching it to the change in kinetic energy is all part of the energy matching. I don't think you can call it friction or a new source of friction.
Well, I mean, there's a starting hypothesis, which is that there's a static regime and there's an inertial frame in which the bubble propagates with constant velocity.
Yes.
And then under this assumption, you get this relation between this driving force coming from the pressure difference and the entropy change. And this means that if this effect is possible, then there has to be this balance of forces. It doesn't necessarily mean that there's always a solution to this condition, I would say, but if you find a solution, then you expect this then there's this balancing seems to tell you that the friction force grows with the velocity square.
Yeah, I guess we'll have to, this is kind of a difficult discussion, but because to have without a board. But that equation matching TZZ across the boundary, I say, is just part of the standard. Yes.
I understand. And the standard treatment, you still have to try to impose all the constraints from the nucleation temperature, the hydrodynamic profiles. I agree.
Yeah.
And that's why also we looked at solutions satisfying, instead of looking at the matching equation, we wanted to look at things locally at the level of the differential equations, either including time dependence or either still in a static wall, but considering the equations at the local level. And we did find solutions, and the friction force, inferred from these solutions is matching this growth with velocity.
Yeah, well, the thing that you call a friction force, but it may not be.
It's a non-dissipative back reaction force. I would, since it's non-dissipative, because as we've seen, there's entropy conservation. Maybe we call it in our paper back reaction force. And well, Konstantin and No called it hydrodynamic obstruction to runaway bubbles.
Yes, that was a bit of a confusing way.
Yeah, maybe the use of friction, I agree, it could be confusing. That's a good point.
Okay, but you say that it's in equilibrium because you don't generate, this is a second question, you say it's in equilibrium because you don't generate entropy.
Yeah.
And that's also a strange feature and a rather special solutions, I think, would not generate.
You don't in principle, there's an assumption that there's some degrees of freedom who have large enough interaction rates, much faster than, let's say, the timescales for this processor are much smaller than the time for passage of the bubble wall. If this happens, these local degrees of freedom, some degrees of freedom will stay locally in equilibrium at every point during the transition of the bubble. And in this case, this analysis would apply. And then depending, so what can happen in a generic case is that for some degrees of freedom, they will be able to attain local equilibrium. And then maybe one has to use a separate treatment for the degrees of freedom for which local equilibrium is attainable. And then for the degrees of freedom which would fall out of equilibrium, for which the standard relation between friction and non-equilibrium effects would apply.
Thanks.
Yeah, thank you very much. I think we have to stop here, although this is certainly a very interesting discussion. If I understand correctly, there will also be a panel discussion again tonight, starting at 6:10, and I hope we can continue parts of this discussion during that session as well. But now we have to move on to the next talk.
Okay, thank you.
Yeah, thank you very much, Carlos. Thanks again. We have to move on to the next and final talk of that session here. by Oliver Gold. Hi, I see you turned on your video already. Excellent.
Hi.
We see your slides.
Great.
Yep. Now they're also full screen. Perfect. Okay,
Great.
so the final talk of the session is by Oliver Gold from University of Nottingham. And Oliver will tell us about reliable predictions for cosmological phase transitions. Please, Oliver.
Thank you very much. Thank you very much for inviting me and for organizing this nice talk. And also thank you to all the previous speakers for their talks. My talk today, many of the important contributions for it have been made by my collaborators. And yeah, you'll see some of these names coming up again. I'm talking, of course, about first order phase transitions, cosmological first order phase transitions. And here I have a nice triptych by Daniel Cutting and collaborators of some simulations of that. On the left, we have the beginning of the first order phase transition where bubbles are first nucleated. After nucleation, they grow, they expand and collide with each other. And in colliding, if there are any fluids about, that creates fluid flows, sound waves and turbulence, as we've heard. And these in turn create gravitational waves. Those gravitational waves after production would free stream and are potentially visible today by gravitational wave experiments. So this is somehow a very exciting topic because it connects something that happened in the very early universe in particle physics, perhaps at the electroweak scale, to something we can see today as gravitational waves. So yeah, allowing us to probe particle physics at these scales in a new way. There may be other observable remnants which I list here, such as magnetic fields and the matter-antimatter asymmetry or topological defects, all of which can come from first order phase transitions, but I'm going to focus on gravitational waves. As a little bit of context for the kind of approach that I'm going to take today, so the title was Reliable Predictions for Cosmological Phase Transitions. I'm sort of trying to think of this as, I'm trying to take seriously the idea that we can really probe beyond standard model physics with these gravitational wave detectors in a way that could in principle be complementary to or even competitive to collider studies, which have taught us so much about the standard model and about BSM physics. So unfortunately, we have to wait a few more years until LISA and TAIG and others will be launched. But in the lead up to that, the aim is to make reliable predictions of the sort that are already standard commonplace predictions for the LHC. This is the pipeline for making those predictions, starting at the top left and going to the bottom right. Yeah, this is taken from this LISA Cosmology Working Group update paper. And here they've taken, at the top left, some particle physics model. It's Lagrangian and its parameters. You could imagine some extension of the standard model with some extra scalars or fermions or whatever it is you like. And in the bottom right, we have the signal to noise ratio for an experiment, such as LISA. What I'm going to focus on, and I guess you've heard, well, of course, in order to learn about a particle physics model from an observation, you need to understand all of these steps in the pipeline, but I'm going to focus on this first step, which is the step which really involves the details of the particle physics model, in which you calculate, for example, the bubble speed, as we've heard, also the alpha, which is this kind of strength of the phase transition parameter. We also need to know the bubble nucleation rate and things like that. Yeah, so how do we make sound or reliable predictions? The place to start is to first understand how reliable current predictions are, what the uncertainties are in them, and how we overcome them. So there have been several studies of the reliability of predictions of gravitational wave spectra from first order phase transitions, and or rather their, let's say, theoretical uncertainties. And it turns out that yeah, the theoretical uncertainties are relatively large. So if you take your favorite model and you take one physical parameter point, and then you calculate the gravitational wave spectrum perturbatively using perturbatively, then the result depends very sensitively on the details of your calculation, which shows that something is going wrong. In this paper here with Juna Kroon, Thomas Tenkinen, Philippe Chichot, and Graham White, some of whom may be in the audience, we did a kind of encyclopedic study of these theoretical uncertainties. We studied many different kinds and tried to work out which were the largest, which are the most important, in which circumstances, and indeed how big they are. This plot here shows the gravitational wave amplitude as a function of frequency for one physical parameter point in one model. And the red band shows the uncertainty, the theoretical uncertainty of the prediction. And that can be compared here to the LISA sensitivity curve. Yeah, as you can see, this one physical parameter point has a pretty uncertain gravitational wave spectrum. Yeah, it's maybe observable or maybe not observable, even at that level, unknown. So let's unwrap a little bit of that. Why is this uncertainty apparently large? I should point out that we weren't the only people to have spotted this, and yeah, several other studies have spotted this kind of large uncertainty. But anyway, so why is it so large? One simple reason is that the gravitational wave spectrum depends very strongly on the parameters, the phase transition parameters. So I mentioned earlier the temperature of the phase transition, and here on the top, this is the change in the trace anomaly across the transition. But the gravitational wave amplitude is proportional to this ratio. It's a dimensionless ratio, and so you might expect the top to kind of scale a bit like the bottom, but actually that's not the case. And so the bottom scales as 8 powers of the temperature, and so it's an increasing function of temperature, whereas the numerator here is a decreasing function of temperature. So as you have more supercooling, you have more heat kicked out, roughly speaking. And as a consequence, this ratio depends really, really strongly on the temperature of the phase transition, even more strongly than T to the 8. And on top of that, or rather, knowing this, you know that you need a pretty accurate measurement, or rather prediction of T star if you're going to get an accurate prediction for the gravitational wave spectrum. And unfortunately, predictions of T star typically are not very accurate. So this is a nice study by Lauri Niemi and others, including David Weir, who will be speaking next. This is a study of the 2 Higgs doublet model. And we have here the critical temperature along the x-axis, just as a number line, and 4 different calculations, including a kind of state-of-the-art lattice calculation, which was a real novelty of this paper. But yeah, typical calculations are more comparable to these red and green lines, which show, again, uncertainty bands for this temperature. And as you can see here, the uncertainty bands are, say, 40 GeV, and they differ from the lattice result by a similar amount, over 100 and something. So they're maybe 30, 40% uncertain. Yeah, and then when you take that to a high power, you get a big uncertainty. To unpack further and to understand where those 40% or 30%, whatever it is, uncertainties come from in the temperature, you have to understand a little bit about high temperature physics. In particular, you have to understand that at high temperatures, infrared bosons become highly occupied. You basically get a condensate, essentially you get a condensate of bosons, and that causes effective expansion parameters to grow and perturbation theory to become more and more difficult, essentially. So if I call here the effective expansion parameter alpha F here, if at 0 temperature you had an expansion parameter which was like G squared, so this is, you can imagine G being a gauge coupling. At finite temperature, that gets multiplied by the Bose distribution, because kind of more modes occupied sort of combined together to give you a stronger coupling. And this Bose distribution, when these two are both approximately 1, this Bose distribution grows. That's when P is small, and it grows like this, so that the effective expansion parameter gets multiplied by T over P, where P is small compared to T. So this is a large number, meaning that your coupling gets stronger. And this, of course, depends on P. So here are the kind of typical scales of thermal physics. There's the hard scale, where P is like T, in which case you just have the same expansion parameters at 0 temperature. There's the soft scale, which is the kind of Debye screened scale. And in that case, P is like GT, and then the expansion parameter grows by essentially the square root of the expansion parameter at 0 temperature. And then there's the ultra soft scale, in which everything becomes non-perturbative. So your expansion parameter becomes order 1, and perturbation theory is no longer any good. A naive attempt at these calculations is rather complicated, because individual diagrams and so on get multiplied by, or infinite classes of diagrams get enhanced versus others. And if you are to do a systematic calculation, the best way to do it is using effective field theory. David Weir will talk about that next, but this is something that I'm going to use throughout in the rest of the talk, which is dimensional reduction and three-dimensional effective field theories of high temperature physics. And this allows you to kind of arrange your calculation based on the hard and the soft and the ultra soft and so on modes, and to calculate order by order in powers of couplings in a kind of systematic and straightforward way. So I talked to you there about why perturbation theory is a little bit in trouble at high temperatures. So what I'm now going to talk to you about is a study, or there have been some other studies, but this is a recent study of comparing the lattice to perturbation theory at high temperatures, and comparing it to relatively high orders to see really how well perturbation theory does or how badly it does. And given that's the focus rather than some specific model, I've picked the simplest model with the first order phase transition. And as I said before, I'm going to use this effective field theory approach using dimensional reduction. So I'm going to be working with a 3D theory, a 3D effective theory. And this is it. It contains one real scalar degree of freedom. It's the simplest theory with the first order phase transition. I put subscript 3 everywhere to remind you that this is a 3D theory, effective theory. And its couplings here, sigma 3, m3, g3, and lambda 3, they're all effective couplings, which themselves can be thought of as functions of the kind of UV couplings of your full theory. So you could imagine embedding this effective theory within the real singlet scalar extension of the standard model, sometimes called the XSM, where you have the standard model, the singlet, and portal couplings, say, between the Higgs and the singlet. And then this sigma 3 here, for example, would be a function of all of these couplings, as well as the standard model couplings and the temperature. So the theme here being lattice versus perturbation theory. This is my lattice slide. Lattice simulations in 3D are significantly easier than the kind of lattice simulations that are done routinely in lattice QCD. And some of the reasons are that, or perhaps the main reason is that these 3D theories are super renormalizable, which means you have exact lattice continuum relations. On top of that, there are efficient update algorithms which are known. So once you're able to set up your lattice, put your fields on it, getting pretty reliable predictions with very small error bars is just a matter of running it and taking continuum limits is fairly easy. In doing these Monte Carlo simulations, you get an estimate for the probability distribution in thermal equilibrium for the Boltzmann distribution. Here I'm showing kind of one slice through that distribution. So probability on the y-axis, and on the x-axis, this phi bar quantity is the volume average of over your lattice of phi. So it's the VEV, or the condensate. And yeah, so this is the probability distribution of that condensate. And you can see in all of these plots, they're kind of two-peaked, showing that there are two phases coexisting. On the left here, as these lines go down, the lattice, the physical volume of the lattice is increased. And as the physical volume of the lattice is increased, these states in between the two phases become more and more exponentially suppressed, while the phases themselves don't change very much. On the other hand, if I keep the lattice volume the same and change the lattice spacing, not a lot happens. This is using these exact lattice continuum relations, you can take the continuum limit fairly straightforwardly. So that was my lattice slide. Here's my perturbation theory slide. So as I said, in 3D, these effective theories are super renormalizable. So things work a little bit differently in 3D. In particular, the coupling constants have positive mass dimension. That's related to that super renormalizability. And as a consequence, the dimensionless expansion parameter of your loop expansion within 3D is a ratio of the couplings to, of the couplings to the mass. So this is the 4-point coupling and this is the 3-point coupling, each of which have different mass dimensions and hence different powers of the mass on the bottom. So this is the loop expansion parameter in 3D. Now, near the critical temperature, the mass can be related to the couplings like this. And hence you find that near the critical temperature, the loop expansion parameter in 3D is this funny combination, which I've called alpha 3. Alpha because expansion parameter, and 3 because we're in 3D. So yeah, it's a ratio of the 4-point coupling to the 3-point coupling. And interestingly, this diverges as you take G3 to 0. The reason being that when you do that, you hit the second order phase transition. And at a second order phase transition, you have a massless particle. And as you can see here, when you have a massless particle, your expansion parameter diverges, perturbation theory breaks down. Actually, I'll show you that for reference. I'll show you going back a little bit. This is this infrared enhancements. When you take P to 0 here, this thing blows up. So that's what's happening at the second order phase transition. Okay, back to where we were. Okay, so that's perturbation theory, that's the lattice. Now let's compare the two for this simple theory. So at the bottom here, I write the perturbative result. Here, this is the tree level result 2, and then each successive loop order gets 1 power of alpha 3. And then the coefficient at each loop order is basically some order 1 number, telling you that this really is the expansion parameter. And then in the plot, I show the lattice results here in black circles with black error bars, which are too small to be seen on this log-log plot, together with the perturbative approximations order by order. And on the x-axis, what's shown is the expansion parameter, this alpha 3. So I'm varying the expansion parameter over at least an order of magnitude, going from weakly coupled in the left to strongly coupled in the right. Here, the expansion parameter is 1, and here it's more than 1. And yeah, on the y-axis, this is the change in the VEV across the transition. This also tells you the latent heat, and it's an important quantity. And what is the take-home message of this this plot is that actually, if we look at this 3-loop result, say, you can see that perturbation theory and the lattice are agreeing really remarkably well up to order 1 couplings, and from more than order of more than an order of magnitude change in alpha 3 and in the strength of the transition. So all the way from strong transitions to relatively weak transitions, high order perturbation theory works very well. There's only a 1% error here. And I should point out though that this relies on renormalization group improvement for these two. Without that, it looks significantly worse.
Oliver, 5 minutes.
Great, great. I won't need them all, I'm doing well. So yeah, what does this teach us about the theory? So as I just said, renormalization group improved perturbation theory is really pretty accurate, at least when you go to sufficiently high orders. So yeah, going back, this is a log-log plot. So for example, here, this one loop result is, I don't know, factor 2 out or something. But yeah, at higher orders, you get more and more accurate. And that's really promising. That shows that we have like really quite reliable results from two different methods, both from the lattice and perturbation theory. The results that I've derived here can be applied to, for example, the real singlet extended standard model, the XSM, as long as you have a transition in the singlet direction. But it's important, of course, I worked with the simplest theory I possibly could, just to see how, you know, how well these kind of approaches work. And one question would be, how well did these approaches work in other theories, in particular, other theories where the 3D effective theory is different. So if we have 2 scale hierarchies rather than 1, so that's where I have both the soft and the ultra soft, basically, yeah, abelian Higgs would be an example of this. A cubic anisotropy model would be an example of this. So to be honest, would the standard model. Anyway, theories of 2 scale hierarchies. Alpha 3 behaves a little bit different, the effective expansion parameter. It goes like the 4th power rather than the half power of your 4D coupling. And that means that things should converge slower still. But given how well things worked in this theory, I think that's not too bad. Further, in non-abelian gauge theories, at some point you reach this ultra soft scale and higher orders are not computable at all. However, the first few orders are still computable. In fact, the first many, 1, 2, 3, the first 4 orders are computable, 4.5. So yeah, I think neither of these are a deal breaker, and I think these methods have shown a lot of promise and should give reasonably reliable results for other theories too. Here's a sign of how well things are working for the gravitational wave spectrum. Here, this is a recent paper with Tuomas Tenkanen, where we worked in this same model, this real singlet extended standard model, and we did a kind of standard-ish 1 loop calculation, which I've here called order G cubed, because 1 loop is accurate to that order. And then we did a 2 loop calculation, which has all the order G4 stuff. And you can see that the theoretical, again, these colored bands are the theoretical uncertainty bands. And you can see that there's a massive reduction in theoretical uncertainty when going up 1 order, suggesting that even though we have these big theoretical uncertainties at the moment in our 1 loop calculations, maybe going a little bit further is enough to significantly improve things. Also interesting that these bands don't quite overlap, and it turns out that 2 loop effects also give a stronger transition. That's something that's been seen over and over again in different models. Yeah, so here are my conclusions. So phase transitions might be observable by gravitational wave detectors. If we're going to make reliable predictions, we need calculational developments. Effective field theory, as you'll see discussed in David Weir's talk, I think provides suitable tools for doing this. And I've shown in this real scalar theory that both perturbatively and on the lattice, everything seems to be working really nicely. And I think there's promise for more difficult theories. As we've seen just then, it seems to working a little bit harder, going to slightly higher orders seems to improve things dramatically. And thanks for listening.
Thank you very much, Oliver. This was very interesting. We have time for a couple of questions.
Can I ask a question?
Yes, sure. Please go ahead.
I'm sorry, I missed the first half of your talk, but I was wondering, how does this improved RG relate to the work of Paul Stevenson, for example? I don't know if you ever heard of him.
I have not. You'll have to tell me the work.
Well, it involved optimizing. I think he called it optimized renormalization group. And he basically just tried to minimize the error in renormalization group. And
yeah, okay, so that is something. So sorry, if I go back to here, that is something that I have used. I have used this optimized RG stuff in these higher order things. One thing I should point out though is that somehow at high temperatures, RG improvement is not possible at one loop. And that's something weird about high temperatures. And that's something that we discussed in this paper, that kind of the first order at which you can get RG improvement at high temperatures is 2 loops.
Okay, interesting. Thank you.
Okay, do we have another question for Oliver? If so, please raise your hand. Okay, no more questions apparently. Then thank you very much again, Oliver. And also thanks again to all speakers here in that session. I think this concludes this session. And I hand it over to the organizers again. Thank you very much, everybody.
Thanks to all the speakers. I'm afraid we only have time for a 5-minute break again. So let's resume at